Hello, my name is Folgesvold Reines. I come from NTNU in Trondheim, Norway, and I'm going to present for you my work, which is based on my project and master thesis, which I just completed. It's titled Analysis and Improvement of a Mathematical Turbine Model. First of all, why do we have to model hydroturbines? So we need to have good and accurate models in order to ensure optimal design of new plants, but also optimal operation of existing plants. We can use models to predict behavior and perform analysis, and that can include stability analysis of the turbine and its governor, or transient analysis of turbine and the waterways, but also logic grid analysis of the entire electrical grid. A mathematical model describes the system of interest with equations, and we can distinguish according to its basis. So a first principles based model is based on physical laws, and we do not have to make any assumptions, while empirically based models are based on experiments and observation, and it's not necessarily supported by theory. Further distinguishing can be linear versus nonlinear, or steady versus non-steady. The former is about the nature of the equations, and the second is about if it includes any transient terms, if time is included in the equations. The turbine model that I've worked with is a first principle based mathematical model that was first proposed by Professor Turbine in his doctoral thesis in 1990. I've worked with a slightly simpler version than what he presented at the time. It's a steady version, so no transient terms, but also excluding empirical loss terms. So there's no empirical coefficients that you need to tune to measurements. It's completely first principle based. I'm not going to perform the entire derivation of the equations. It's quite long, but the starting point is the Euler turbine equation and the definition of turbine opening degree, together with the velocity diagrams at the runner inlet and the runner outlet, which you can see here in the figure for Francis turbine. These velocity diagrams are slightly off the best efficiency point, as you can see from the swirl component here, and also that the relative velocity does not match the runner blade fixed angle here. So this is a starting point for the model. The governing equations of this model are one equation for the flow rate or the head and one for the mechanical torque on the shaft. All of the parameters in these two equations are non-dimensionalized with respect to their best efficiency values. That's the rated values. So Q here is the flow rate, Y is the opening degree, and H is the net pressure head, omega is the rotational speed, and T is the mechanical torque on the shaft. So sigma here is a geometrical constant, which is defined by the main dimensions and the best efficiency point of operation. Ms is a specific starting torque. It's the non-dimensional torque when the rotational speed is 0. And from these two equations, for the flow or the head and the torque, you can define the turbine efficiency, also in non-dimensional terms, by inserting the torque equation and the head equation into the numerator and the denominator, and then you get this expression, which is very relevant because I have looked a lot into how this model predicts the turbine efficiency and how it captures different types of losses occurring in the turbine. I also want to present for you the linearized equations. Here is the linear flow and torque equations, where the A11, the A12, and so on are the characteristic coefficients. They are the partial derivatives of the dependent variables with respect to the independent variables in a certain point of linearization. So this linear version of the model is applicable when you want to look at small deviation in one parameter. How does this change affect the other parameters? This can be used, for instance, in stability analysis. I used it in the simulation software Simulink, where I set up block diagrams and simulated small deviations in frequency and small changes in opening degree. I'm not going to talk much more about the linear model, but I just wanted to show it to you before I move on. So it has been demonstrated in previous works how this model captures different losses, how well can it predict the turbine efficiency. And a really nice way to present the turbine efficiency is in the hill diagram, the hill chart, where you have flow on one axis and speed on the other, and you are plotting lines of constant opening degree together with curves of constant efficiency, where these curves form a hill towards the point of best efficiency, which is here where the red dot is now. So this turbine model managed to capture the efficiency and the different losses quite well along the lines of constant opening degree. That means along the speed axis, but it does not capture losses so well along the flow axis. This means that irreversible loss phenomena like viscous effects, turbulence due to suboptimal inflow angles, residual swirl in the draft tube, and so on, they are not captured that well. And the improvement to this weakness that I have looked more into is to include the incipient efficiency, eta E. In the first iteration of this model, these losses are captured by including head loss terms, and these head loss terms are subtracted from the torque equation. But with the incipient efficiency, we are multiplying the eta E into the torque equation, as I have demonstrated here. So in that way, we also get the incipient efficiency in the efficiency expression here. And in that way, we are including more of these irreversible losses. Now, the incipient efficiency can be any mathematical loss function, and there should be one function for any turbine that will make these equations correct with respect to measurements. So I looked into how the model performs without any improvement. That is the same as setting eta E equal to 1. I also looked at the very simple parabola function, which you see here. It's very simple, but it does contain the most important physics. But most importantly, I looked into making best fit functions to measurements. Now I accessed measurements at rated speed and rated head for one high head, one medium, and one low head turbine. And I fitted to these measurements curves. Now this one is for the high head, it's a polynomial. This is for the medium head, it's actually a Fourier series. And this one is for the low head turbine, it's also a polynomial. And the exact functional expressions are not so relevant, but the point is that I insert these functions into the model and look at how does this improve the overall model performance, not only at rated head and rated speed, because obviously it does improve, it's been tuned to measurements, but also at other points of operation. In order to set up the model, you need these three inputs. This is the guide vane angle at the best efficiency point. Sigma here is the geometrical constant containing information about main dimensions and the point of best efficiency, and it's also very important for the self-governing properties of the turbine, the relations between speed and flow. And then there is psi, the machine constant that was determined by the velocity diagrams at the point of best efficiency. Now I used the model equations to calculate characteristic curves, and I set together these curves to form hill diagrams. And I calculated using the model both without an incipient efficiency and with the incipient efficiency that I proposed in the previous slides, the polynomials and the Fourier series. And these hill diagrams I compared to the measured hill diagrams from the experiments. And all of this work I did in MATLAB, and I'm going to present to you in the next slides. Here you can see the hill diagrams for the Hyatt-Francis. Now the area of measurements, it's not that big, but we can still make a few assessments of how the model performs for this turbine. First of all, the characteristic curves of constant opening degree, the flow speed curves, are predicted quite well, and they are completely unaffected by the presence of eta E because eta E is inserted into the torque equation, but it is the flow equation that predicts these characteristics. And when it comes to the hill shape, as we expect from previous, there is a lack of slope here and here. The vertically slope is not really present when you don't include the eta E, but when you do include eta E that goes towards 0 for high and low flow, you do get much more of a slope in these areas. Even though the measurements does not contain that much information about the zero efficiency line, also called the runaway curve, which you see here, we can still make a few assessments about how the model performs, because the model predicts a horizontal area and a vertical area, and this is not really what we expect. Now, for the medium head Francis turbine, I accessed a little bit more experimental data. For instance, we do see a really clear runaway curve here, which makes us able to assess the model's runaway curve. Now, if we go into detail, the area here where we have approximately rated speed and a very low flow, a very low opening degree, the model, including an incipient efficiency, performs quite well. This is also the case if we go into the y equal to 1, that means the rated opening degree, and we find the runaway condition there. That is also quite close predicted by the model, but the area in between here, this is less accurate than what we see here. But even so, we do see that the general improvement of the hill shape, as we saw for the Hyatt-Francis, the incipient efficiency makes this much better, and around the peak, the model performs really well. Finally, here are the hill diagrams for the low-head Francis turbine. Now, this turbine has almost completely flat characteristic curves for constant opening. They resemble what we expect for a Pelton turbine, where the flow rate is almost independent from the speed. It only depends on the head and the valve opening. And from the model equation, it was sigma, the geometrical constant, that determines this relationship. And when sigma is almost 0, there is almost no dependency of the flow rate upon the speed, such that these characteristic curves are flat. Moving on, the hill shape is altered a lot by including incipient efficiency. This is because the eta E was very steep. It was fitted to measurements, so they were quite steep. And that's why we see a big difference here and here with respect to how the model performed without eta E. As discussed for the other turbines, there is something wrong with the runaway curve by the model. Here we have both the vertical and the horizontal area, but the little that we see of the runaway curve from the measurements, it has a finite slope, so the model does not resemble what the measurements show. But apart from that, around the peak, model performs quite well when you include the improvements. So we can make a few common observations from these hill diagrams. First of all, the model equations, including a smooth incipient efficiency curve going from 0 through 1 and then backing into 0, will produce a hill diagram that is shaped similar to a cone with a rectangular base. Now, along the constant opening lines, that means along the speed axis, the equations already performed quite well. They already captured a lot of losses, but they did not capture that much losses along the flow axis for constant speed. So this was the drawback that we intended to correct for with the eta e function. And we did see that depending on what eta e curve you choose, you will change the hill shape a lot. But we did also see that we could not make the runaway conditions and the runaway curve correct. It was inaccurate in the area between where we have the rated speed and low flow, or the area where we have the rated opening and the high speed. So in this area, the model predicts quite inaccurate runaway curve. I looked a lot into this issue and why the model doesn't capture it that well, and probably we need to have loss models that also functionally depend on the guideway and opening directly, and also on the runner speed. Probably the dependency of eta e only on flow rate is not enough to capture this. I also looked a lot into how we can generalize this function, because at this point I only tuned it to measurements, I fitted it to measurements, but if you cannot assess measurements, if you don't have any measurements, it would still be nice to generate an incipient efficiency curve. So what I did was that I looked at the tendencies. I mean, we saw that a high head had a much flatter curve than a low head turbine. So I looked into having a generalization based upon the turbine speed number, the specific speed, because the specific speed can relate the nominal head, flow, and the runner in only one single dimensionless parameter, and this parameter is quite convenient. So for a higher specific speed, you will have a sharper incipient efficiency curve, and for a lower specific speed, you will have a much wider one. I'm not going to go more into detail about this, but just so you know, there is a possibility to generalize this and get curves without having measurements before. To make a few conclusions of this presentation, the mathematical turbine model that I analyzed and attempted to improve, it's physical correct because it's based on a first principle approach, but this doesn't mean that it's going to be accurate for any turbine. However, it requires very few inputs from only the main dimensions of the runner and the point of best efficiency, so it's very easy to set up. I presented the modified formulation of these equations, including the incipient efficiency, and by choosing the incipient efficiency function wisely, for instance, if you can do a curve fit like I did, the model will perform well around the efficiency peak and along the line of nominal opening degree and the line of nominal speed. But in the area in between and far away from these, the model performs less accurate. For instance, the runaway curve was less accurate. This all implies that the model, as it is, it's suitable for stability analysis, and then you can actually use the linear version if you want to. But for more general transient analysis, for instance, for modeling load rejection, startup shutdown, it's less suitable as it is, and probably it needs some more refinements to perform better on this area. Okay, that's all I had. Thank you for listening.